So when you think about nature and technology, there are striking similarities. Many of the inventions that we know of today were first inspired by nature itself. Mathematics has always been one of the best languages that allows us to understand and describe the world around us, but for a long time we've almost never been able to directly apply equations to the complex geometric structures and formations that we see around us. It just didn't seem possible that the convoluted mountains, clouds, and trees that we see every day could possibly be described using mathematics. Well, after the late 20th century, however, that all changed. With a new form of mathematics called fractal geometry, suddenly to us, nature consisted of these exciting patterns, and those patterns could be represented as equations. The concept of fractal geometry began as far back as the 17th century, but the actual coinage of the term fractal and the mathematics behind fractal geometry didn't come into existence until the 1960s, when they were established by a French mathematician known as Benoit Mandelbrot. And as Mandelbrot pointed out, no matter how far you zoom into a fractal, you always see the same exact pattern. And this concept is known as self-similarity. Now, when you look at nature, you can distinctly see the fractal patterns and concept of self-similarity. As examples, here I have broccoli, as well as a snowflake. After further research, scientists and biologists made even more fascinating discoveries. They found that the beating of a healthy human heart follows a fractal rhythm. They also found that the blood flow of healthy tissue exhibits a fractal pattern, while the blood flow of cancerous tissue is distorted and tangled. And in just a short while, the rules and methods that govern fractal geometry would be applied to design aberrant antennas. It was Dr. Nathan Cohen, a Boston radio astronomer, who invented the idea of the fractal antenna in 1988. And here's a picture of one of his very first patents on fractal antennas. Also, here is one of the very first fractal antennas he constructed, and believe it or not, this is actually for the 10-meter amateur radio band. Today, fractal antennas have been used and are still used in a wide variety of applications. They've been used in ham radio antennas, cell phones, radio frequency identification, and you can see on the left the size reduction of the fractal antenna compared to the design on the right. And fractal antennas have even been used in missiles. But don't get any ideas. The concept of fractal geometry begins with what's called a repetition of a motif, or the abstract idea of self-similarity. To make a fractal work, you begin with a single basic shape, or initiated. And this could be any shape you want, from a straight line to a pyramid. Then you select what's called the generator. And again, this could be any shape you want. In this instance, it is an equilateral triangle. And the generator marks the first iteration of your fractal. Then what you do is you add iterations. And you can see by doing so, I take smaller copies of the generator and add them to the iterator. And especially here, you can see that these smaller triangles are branching outward from the larger ones. There are two observable methods that can be distinguished by generating fractals. In the first method, you maintain the same overall size or area of your fractal, so that after each iteration, you exponentially increase the perimeter length of your fractal antenna. And once again, here you can see on the left I have my generator, and I'm merely taking smaller copies of that and adding them to the iterator. Now, whereas before in the first method, you maintain the same overall size or area of your fractal antenna, in the second method, you maintain the same overall perimeter length of your fractal antenna, so that after each iteration, you shrink the overall size of your fractal antenna after each cycle. So you can easily see why either two of these methods would be favorable in designing antennas. There's an interesting phenomenon when it comes to fractal antennas, and that is the effect of adding iterations. Fractal antennas are naturally multiband, especially at higher frequencies, and this is attributed by their unique geometric structure, as well as the effect of adding iterations. So as an example, let's consider a simple quad loop antenna. And when it comes to any antenna, you want the incoming power from your radio or your transmitter to be fully radiated by your antenna. And the dip on the graph here indicates the least amount of reflected power for the antenna. So you'll notice that there's nothing intrinsically special about this antenna. But take a look at what happens when I add an iteration. All of a sudden, you can see that this antenna is tuned for yet another frequency. Likewise, as I continue to add more iterations, it affects the multiband behavior of the fractal antenna. But note, however, too many iterations can often be redundant, and this actually can mitigate the performance of your fractal antenna. Iterations also affect the 3D radiation pattern or field strength of your antenna. So watch what happens when I go from the third iteration to the fifth iteration. You can see that more directivity is evident within certain sections of the field strength pattern. And because of these different methods and phenomena, fractal antennas have very many advantages. They give us the ability to maximize the perimeter length of the fractal antenna within a given area, and this feature can make fractal antennas very compact. They are naturally multiband and wideband, especially at higher frequencies. And here's an animation showing the multiband behavior of fractal antennas. You can see that different sections of the fractal antenna are resonant at different frequencies. Fractal antennas also allow for simultaneous operating on multiple frequencies. They exhibit an effect called fractal loading, and this effect emulates discrete inductors and capacitors, which in turn can reduce the overall size of your fractal antenna. And normally you would have to use capacitors and coils to produce the same effect with other types of antennas. And they have low mutual coupling, which means that if you were to place two or more fractal antennas side by side, it wouldn't affect the performance very much. And they allow themselves to be easily integrated onto printed circuit boards. Fractal antennas also have a few disadvantages. The complexity increases as you add more iterations, and this can make it more difficult to perform calculations on your antenna as well as construct the final design. Also, impedance increases as you add more iterations, so sometimes you might require a matching network, such as a gamma match, to properly load the antenna under test. And of course, lower frequency fractal antennas are a little bit more difficult to design and build due to their length requirements. But let's not dwell on the disadvantages too much. The important thing is to consider whether or not fractal antennas are suitable for your application. They can't be expected to meet every application or demand, but their advantages strongly point out just where they can be useful. So as an example, suppose you have a teenager that has GPS running in the background, a YouTube video loading, and he or she is sending text messages. There are a couple of problems here. To begin with, teenagers spend way too much time on their cell phones already. The second biggest problem is the question of how you can maintain simultaneous operation over a wide range of frequencies and still keep the antenna compact. Clearly, a scenario like this is not very practical. When it comes to fractal antennas, normally you only need one antenna. You can operate on multiple frequencies at once, and you can keep a compact design in the process. In fact, it is quite possible that in the future, fractal antennas will be absolutely essential in the development of mobile technology. Also in the future, fractal antennas may offer the possibility of optimized design in which a unique fractal pattern or shape would be used to accommodate stringent requirements in an application. And those requirements may include that the antenna has to be very compact or operate on specific frequencies. So how do you go about designing a fractal antenna practically and efficiently? After researching online, I wasn't able to find a single source of free, reliable software that would allow me to design and construct fractal antennas practically and efficiently. At first glance, fractal antennas do seem quite complex. There are thousands of different designs you can try, and those designs can be very confusing. But the truth is, fractal antennas don't have to be quite as complex as most people think. There are a few simple design tools that you can use to help you get started. One of the very first design tools you can use is a programming language, and this is incredibly useful. It can do anything from rendering fractal antennas to exporting the XYZ coordinates of fractal antennas to a Gerber file so they can be prepared for a printed circuit board. Another useful tool is antenna modeling and optimizing software, and this allows you to simulate a hypothetical fractal antenna for your application. And one example would be Fornet 2. After that, it's simply a matter of constructing the antenna, and to do that, you can use free PCB CAD software that is available online, such as Eagle or Express PCB. In order to bring together the theoretical and practical aspects of designing fractal antennas, I wrote a program written in the Python language that generates the coordinates of 5 conceivable fractal antennas and writes those coordinates to a special file called a .nec or net file that allows me to analyze and simulate fractal antennas. And by using the Fornet 2 simulator and optimizer program, it became incredibly easy to perform spectrum sweeps, twirl an antenna 3-dimensionally, observe the 3D radiation pattern, and invoke matching networks. Of the 5 conceivable fractal antennas, I chose to focus on 2 in particular, including the single Koch-curve fractal antenna and the single Hilbert curve fractal antenna. And the very first step for me was to generate a suitable candidate for the single Koch-curve fractal antenna that would eventually be built in real life. So after tweaking my program a little bit and fiddling with the simulator, the first candidate was finally ready. And here's a picture of its physical construction. The dimensions of this antenna are 0.67 feet by 2.5 feet. And the dimensions of this antenna were completely derived from the simulated results. And brace yourselves, because here are the simulated results. What you see here is the 3-dimensional radiation pattern or field strength of the Koch-curve fractal antenna. And the red and violet colors indicate a higher magnitude of field strength. So you'll notice that this pattern is a lot like that of a common dipole antenna. And here's the azimuth pattern of the Koch-curve fractal antenna. And just so you get an idea of how the Koch-curve fractal antenna compares to a dipole, here is the 3D radiation pattern of a dipole. And you can see that it's very, very similar to the Koch-curve fractal antenna 3D radiation pattern and also the azimuth pattern. So the next step for me was to perform a spectrum sweep. And by doing that, it would tell me where the antenna was close to being present. And here's the results of the simulated spectrum sweep. And once again, the dips in the graph indicate the least amount of reflected power, or those are the points at which the antenna is resident. So you can see that this antenna would work well for 146 megahertz with a 1 to 1.54 SWR. And this is in the 2-meter amateur radio band. You can also see that this antenna would work well for 414 megahertz with a 1 to 1.34 SWR.